right, let's dive straight into this explainer. We've all looked at a globe, right? We see this giant blue marble and think we have an endless supply of water. But the reality of what we can actually drink? Well, that's a very different story. Today, we're unpacking the science, the very real challenges, and a genuinely fascinating technological solution that could literally change the world: hybrid solar desalination. So, Earth's surface might be 71% water, but here's the kicker. Merely 2.5% of all that water is fresh water. And to make things even tighter, a massive chunk of that tiny percentage is locked away in polar ice and deep subterranean reservoirs. We're essentially dealing with an illusion of abundance.
And this sheer scarcity has real-world consequences. Today, over 1 in 6 people globally lacks adequate access to potable water. 1 in 6. This isn't just a minor inconvenience, it's a full-blown global health emergency. Figuring out how to efficiently extract and purify the salt water we do have in abundance, it's no longer a luxury, it's an absolute survival imperative for us.
Part 1. Modern desalination methods. Historically, we've relied on a few main ways to get the salt out. Traditional reverse osmosis, or RO, is a big one. It literally forces water through a membrane using intense pressure. Then you have electrodialysis, which uses electrical potential to physically drag ions away. Hydration relies on forming hydrates at specific low temperatures, like 20 degrees Celsius, and really high pressures, around 30 bar. And finally, thermal methods, like multi-stage flash, which basically just boil and evaporate the water. But here's the catch. Whether you're using extreme pressure, electricity, or extreme heat, all of these methods share one massive drawback. They demand an incredibly high amount of energy to operate. And when we talk about deploying traditional reverse osmosis in remote areas, the true killer isn't even just the huge energy requirements or the greenhouse gas emissions. It's something called membrane fouling. See, that massive pressure shoves salts and minerals straight into the membrane's pores, completely clogging them up over time. Replacing those membranes is incredibly expensive, which makes the whole system super prone to failure in isolated places that don't have dedicated maintenance teams on standby.
Part 2. The hybrid solar solution.
Enter membrane distillation. It's such a fascinating approach because it gives us robust purification without those extreme energy-hungry pressures. Instead of violently forcing liquid water through a barrier, it uses mild heat to create vapor. Only the pure water vapor actually passes through the microscopic pores of a hydrophobic membrane. All the salts and contaminants, they just get left behind.
Now here's where it gets really exciting. When you pair that technology with the sun, everything changes. By coupling membrane distillation with renewable solar energy, or even waste heat captured from other industrial processes, we get a hybrid system. This setup is both economically and environmentally sustainable. You're significantly lowering greenhouse gas emissions and drastically slashing operating expenses, which makes it an absolute game changer for small, decentralized, remote communities.
Part 3. Case study. An Binh Island.
To see how this works in the real world, let's look at An Binh Island in Vietnam. It's the ultimate test environment. We're talking about a tiny, isolated island, just 0.69 square kilometers, home to about 450 people. The critical detail here: they have absolutely zero natural groundwater. None. To make matters worse, their traditional RO plant completely failed because of that exact membrane fouling we just talked about. This forced the residents to rely entirely on incredibly expensive freshwater shipped in by boat from miles away.
So researchers stepped in to solve this. They built an air-gap membrane distillation system, or AGMD. And the best part? It's powered entirely by the island's existing photovoltaic solar panels. The physical setup relies on a cool feed water tank, a hot oil bath for heating, and the core membrane modules themselves.
Part 4. Testing membrane distillation.
The secret sauce for the system's efficiency is actually hidden right inside these modules. They use these remarkable spiral-wound units provided by a company called Aquastill, and they are masters of spatial efficiency. By winding the evaporator, coolant, and distillate channels into a tight spiral, they managed to pack a massive 77.7 square meters of active membrane surface area into just 3 really small cylindrical units. Let's walk through how the water actually flows. The really clever part here, actually, scratch that, the absolutely crucial part is how the cool seawater captures the latent heat of the condensing vapor. As the cool seawater flows in, it literally absorbs the heat being released by the freshwater vapor condensing on the other side.
This naturally preheats the feed water before it even reaches the hot oil bath. It's dramatically recycling energy back into the system and slashing the total energy required to run the whole process.
The researchers tested a bunch of different variables to find the system's sweet spot, and the results were staggering. When they bumped the evaporator inlet heat up from 50 degrees to 70 degrees Celsius, the system literally doubled the freshwater output to 46 liters per hour. At the same time, it drastically slashed the specific energy consumption from about 140 down to just 91 kilowatt hours per cubic meter.
They also tweaked how fast the water was moving. Pushing the water circulation rate to 360 liters per hour turned out to be the optimal balance. This specific flow rate maintained the perfect temperature difference between the hot feed and the coolant. And remember, that temperature difference is the true driving force that pulls the vapor across the membrane. Now, we do have to objectively note a scientific trade-off here. These modules are actually capable of moving water faster, but the system is intentionally designed to maintain a lower water flux. Why? Simply to permanently avoid the fouling and wetting that completely ruined the island's previous RO plant. By accepting a slightly lower output speed, they guarantee the long-term reliability of the system without needing constant expensive maintenance.
Part 5. Proving economic feasibility.
So the team ran a continuous 7-day extended pilot test, and the hero metrics are incredible. The system ran flawlessly during the daytime, using only solar energy. It consistently produced about 45.8 liters an hour of highly pure water, maintaining an incredibly low electrical conductivity of just 39 microsiemens per centimeter. With zero heavy metals or total organic carbon, it fully met the strict Vietnamese potable water standards.
But here is the jaw-dropping economic reality of what this science achieves. For the residents of An Binh Island, importing fresh water was costing them a staggering $50 per cubic meter. This solar-powered pilot system slashed that cost down to just $20.50. That is more than a 50% reduction in the cost of basic survival, utilizing nothing but the ocean water surrounding them and the sun above them.
This incredible success on one small, isolated island leaves us with a profound question. If this localized, hybrid microsolution works so perfectly for An Binh Island, cutting costs, saving energy, and avoiding all the usual pitfalls of traditional desalination, how quickly can we scale and deploy this technology? How fast can we secure clean water for the other 1 in 6 people around the world currently living without it? That is a challenge worth solving. Thanks for joining me on this explainer, and keep questioning the science that shapes our future.